start, let's talk about feedwater heaters. These are devices used in power plants to increase boiler efficiency by preheating the feedwater. This preheating process has two main benefits. It reduces thermal stress on the boiler and significantly enhances the efficiency of the Rankine cycle, the core component in thermal power plant. So, feedwater heaters serve a critical components in power plant by preheating the water before it enters the boiler. They reduce the energy required to convert water into steam. This improvement in thermal efficiency lowers fuel consumption and also operating costs. So these are two primary types of feedwater heaters. The first one is open feed water heater, OFWH. This is a direct contact heat exchanger where steam and feed water come into direct contact to exchange heat. The second one is closed feed water heater, CFWH. In this case, steam and feed water are kept separate with heat transferred indirectly through the tube walls or other surface. So next, here is the working principle for open feed water heater. In this type, steam mixed directly with the feed water in a chamber. This process not only ensures thermal equilibrium but also helps removing dissolved gases like oxygen, which can cause a corrosion. So over here is the process. So the steam is extracted from the turbine and enters the heater. Then inside the heater, the previous pumped feed water is mixed with the steam. The result is a saturated liquid that exits at the pressure of the heater. So this direct mixing is the key of open feed water heater, making it efficient and making it efficient for certain application. So next, let's move on to the closed feed water heater or CFWH. So in the system, heat transfer occurs indirectly. The steam does not mix with the feed water. Instead, it transfers heat through the walls of tube or similar surface. And for the process, steam enters the heater and condense on the outer surface of the tube. Meanwhile, feed water flow inside the tube and absorb heat from the condensing steam. The condenser steam exits as a saturated liquid, often requiring pumping to another part of the system. While this design is more complex and costly than the open type, it is more efficient and suitable for higher pressure system.
Here is a practical example of the ideal reheat regenerative Rankine cycle focusing on closed feed water heater. The system will analyze three major components. First is one closed feed water heater, one open feed water heater, and a reheater. The question is to determine the fraction of steam extracted from the turbine and evaluate the thermal efficiency of the cycle. As seen in TS diagram, water enters the boiler at step 6 as a compressed liquid. It is heated to state 7 where it becomes saturated vapor and further superheated to state 9 at 600 Celsius and 15 megapascal. The superheated steam then enters the high pressure turbine, expanding isentropically to state 10, where the pressure drops to 4 megapascal. At this point, the steam is reheated at constant pressure to state 11, returning to 600 Celsius. Next, the reheated steam expands further in the low pressure turbine. At state 12, 0.7 megapascal, some steam is extracted for the open feed water heater while the remaining steam expands to the condenser pressure of 10 kilopascal, reaching state 13. In the open feed water heater, the extracted steam at state 12 mixes with the feed water from pump 1 state 2. The mixtures exist as saturated liquid at state 3, 0.7 megapascal. Meanwhile, steam extracted at state 10 condensed in the closed feedwater heater, releasing heat to preheat feedwater from pump 2. The condensed steam is then pumped back to the boiler pressure at exist at state 6. Finally, the remaining steam from the low pressure turbine of state 13 enters the condenser, where it condenses into a saturated liquid at state 1, completing the cycle. Here is the data given. We know the cycle operates at the following pressures. The temperature at state 9 and 11 is equal to 600 Celsius. At state 6, the water is in saturated liquid phase at 15 megapascal. From this point, we can continue analyzing state 1 to 13 in the cycle. For each step, we use the provided pressures to look up enthalpy, entropy, and specific volume in the steam tables. But in the state 12, we need to double interpolation to get the value of enthalpy. In the closed feedwater heater, a portion of steam is extracted from the turbine and used to heat the feedwater. This improves the overall thermal efficiency of the cycle by reducing the amount of fuel required to achieve the same steam generation. This ensures that the energy entering the system equals to the energy leaving the system, accounting for the extracted steam fraction Y and the enthalpy of each state. In summary, the closed feedwater heater utilized that Y equal to 0.774, which is 17.74% at 4 megapascal of the turbine steam to preheat the feedwater efficiently. The steam is extracted from the low pressure turbine at 0.7 megapascal to mix with the feedwater, improving its temperature before entering the next stage. The extracted steam fraction Z is used to mix with the feedwater, raising its temperature before it enters the next stage. This process reduces the heat required in the boiler, improving the thermal efficiency of the Rankine cycle. After calculation, we find Z equal to 0.1430. This means that 14.30% of the steam is extracted for the open feedwater heater. Last but not least, once all states are analyzed, we can calculate the thermal efficiency by the equation 1 minus Q out per Q in, which is equivalent to 50.03%.
So next we go to the question example of open feed water heater. This is the question given. The condenser at pressure 7.5 kilopascal after entering the turbine at 20 megapascal and 800 Celsius at a pressure 1.2 megapascal. Some steam exit the turbine and enters the open feed water heater. So from the question above, we must find Y6, that is mass, and the thermal efficiency of the cycle. So, first step, we must draw the TS diagram, follow the information given. 7.5 kilopascal for this area, 1.2 megapascal, and the 20 megapascal. Beside the TS diagram, this is the flow diagram of a turbine, pump, condenser, open feed water heater, and a boiler. Next, below TS diagram, this is a formula we'll use to get Q in, Q out, W in, and W out. Next, we carry out all information from the question. P4, P5 equal to 20 megapascal. P1, P7 equal to 7.5 kilopascal, P6, P3, P2 equal to 1.2 megapascal. Temperature 5 is 800 Celsius. This is a formula thermal efficiency 1 minus Q out over Q in. So we go to the first step. So we can see the point 1 on the line, saturated line in the S diagram. So assume the point 1 is a pale saturated liquid. We can take directly value from saturated table on the pressure table. So the second step, we know second step is isentropic process. So we can assume S1 equal to S2. We must compare the value S2 on the SF at 1.2 megapascal So we get S2 less than SF at 1.2 megapascal. Assume the paste is a compressed liquid, then we use the formula of W pump 1 equal to V1 multiplied by P2 minus P1 equal to H2 minus H1 and get the value of H2 is a 169.662 kilojoule per kg. Third state, that same cases with state 1. We can take VF, HF, SF directly from the saturated water table at P3 equal to 1200 kilopascal. So H3 equal to 798.65 kilojoule per kg. Next, fourth state, this is also isotropic process. S4 equal to S3. The paste is a compressed liquid. We can find H4 following the formula of our W pump 2 equal to V3 multiplied by P4 minus P3 equal to H4 minus H3 and get the answer. H4 is X to 0.06 kilojoule per kg. State 5, we know T5 bigger than T saturated at 20 megapascal, so we can categorize that paste in superheated vapor. So refer table superheated vapor at 800 Celsius in 20 megapascal, we get the H5 equal to 4069.7 kilojoule per kg. State 6 is paste is superheated vapor because when we compare the pressure 6, which is 1.2 megapascal on the saturated table, we can see S6 value bigger than SG at 1.2 megapascal. After that, we must refer superheated vapor table and do interpolation. So we get S6 equal to 3056.36 kilojoule per kg. So for the state 7 is a isotropic process. S7 equal to S6. Then we compare the with saturated table on pressure 7.5 kilopascal. We get S7 between SF and SG. So we must find the quality X to get H7. So value of X7 is 0.844. So we put the X value on the H7 equal to HF plus X HFG and get H7 value equal to 2199.454 kilojoule per kg. Lastly, we get all answer for H1 until H7. We can find mass Y6. So the formula energy in equal to energy out. Follow the flow diagram above. We can get the formula Y multiply has enthalpy 6 plus 1 minus Y multiplied by H2 equal to H3. We get the value of Y equal to 0.2176. For the thermal efficiency, we can find Q in and Q out, and the value is thermal efficiency is 0.511 or 51.1%.
Next, I will be explaining the advantages, disadvantages and application of both types of feed water heaters in power plants. Let's start with open feed water heaters. Here are some key advantages. For the first advantages is simple design. Open feed water heaters have a straightforward construction which makes them easier to design, build and maintain. This simplicity reduces the likelihood of mechanical issues and simplifies repair. Second, lower cost. Due to their uncomplicated design, open feed water heaters are generally cheaper to install and operate. Then they require fewer materials and less labor for construction, leading to cost saving. Third, direct contact heating. In open feed water heaters, water is heated directly by steam. This direct contact allows for efficient heat transfer, as the steam condenses directly into the feed water, transferring its heat energy quickly and effectively. Lastly is air removal. These heaters help remove non-condensable gases such as air from the feed water. This is important because non-condensable gases can reduce the efficiency of heat transfer and causes corrosion in the system. Now let's look at the advantages of closed-feed water heaters. First, higher efficiency. Closed-feed water heaters operate at higher pressures, which enhance the heat transfer process. This results in better overall efficiency for the power plant as more heat energy is captured and utilized. Second, reduced corrosion. Since water heat and steam do not come into direct contact in closed-feed water heaters, there is less risk of corrosion. This is because the feed water is contained within tube and the steam flow around these tubes, preventing any direct missing. Third, heat recovery. Closed-feed water heaters are excellent at recovering heat from turbine exhaust steam. By capturing and utilizing this heat, the overall efficiency of the power plant is improved, leading to energy saving. Lastly is compact design. Due to their design, closed-feed water heaters are generally more compact than open-feed water heaters. This makes them ideal for power plant with limited space, as they can be installed in smaller. For the next slides, I will be present the disadvantages of both feed water heaters. First, I will present about the disadvantages of open feed water heater. First point is limited efficiency. Open feed water heaters generally have lower efficiency compared to closed system. This can result in less effective heat transfer and overall energy loss. Second, size and space. They require more space for installation, which can be a constraint in some power plants where space is limited. Third, heat loss. Due to direct contact between steam and water, there's more potential for heat loss in open feed water heaters. This can affect the system overall performance. Lastly is operational complexity. Managing water levels and maintaining optimal operation can be more challenging in open feed water heaters, requiring careful monitoring and control. Next, let's look at the disadvantages closed feed water heaters. First is higher cost. Closed feed water heaters are more expensive to install and maintain compared to open feed water heaters. The initial investment and ongoing maintenance costs can be significant. Second is complex design. The design and construction of closed feed water heaters are more complex, requiring specialized materials and expertise. This can lead to higher engineering and construction costs. Third is corrosion risk. Although the risk of corrosion is reduced, it still exists due to the presence of condensates. Proper material and maintenance are required to minimize this risk. Lastly is maintenance challenges. Maintenance and repair can be more difficult and costly due to the close nature and high pressure operation of these heaters. Assessing internal component for repairs can be a challenge. Now, I will explain where each type of feed water heater applications. Let's start with open feed water heaters. First, smaller plants. Open feed water heaters are often used in smaller plants, power plants, or industrial facilities. Their simpler design and lower costs make them an attractive option where the investment in more complex system is not justified. Second, all plants. You will frequently find open feed water heaters in older plants. Their simpler design and lower initial costs have made them a popular choice historically. Third, low pressure system. These heaters are ideal for system operating at lower pressures, where the efficiency gains from closed feed water heaters are less significant. Their straightforward design fits well with the needs of low pressure system. Now let's move on the closed feed water heater. For the first point is large power plants. Closed feed water heaters are widely used in large, modern power plants. These plants require high efficiency, and closed systems help achieve this by operating at high pressures and better heat transfer rates. Second, high pressure system. In high pressure steam system, maximizing thermal efficiency is crucial. Closed feed water heaters are essential in this system, helping to improve overall plant performance. Third, heat recovery systems. These heaters are integral in system designed to recover heat from turbine exhaust steam. By capturing this heat, they enhance overall efficiency, making them a key component in modern power plant. Lastly, chemical and petrochemical industries. In industries where precise control of feed water temperatures and quality is necessary, closed feed water heaters are utilized. Their ability to maintain tight control over these parameters makes them invaluable in such setting.
So for conclusion, how efficiency is improved by using regeneration and reheating, the system makes better use of the heat, leading to a noticeable boost in thermal efficiency. By the understanding the role of feed water heaters, the closed feed water heater, or known as CWH, works efficiently because it keeps the heat exchange separate, but requires more precise management of pressure difference. So next, on the other hand, the open feed water heater, or OFWH, simplifies the design by mixing steam and water directly, which make heat transfer very effective, but demands careful attention to maintaining matching pressure. Why it matters? Combining reheating and regeneration techniques allow the cycle to achieve thermal efficiency of 49.1%. This demonstrates how advanced Rankine cycle designs can significantly reduce energy waste and improve overall performance.